mic if you need to ask something or clarify something. Problem like that one here. Okay, maybe let us start with reduction gearboxes. Right, so we are going to first look at reduction gearboxes. Right, under reduction gearboxes, we have looked at the first section basically. Right, I think I gave you exercises to practice with. Right, on those exercises, this is the only type of problem based on reduction gearboxes that you haven't really touched on. Right? Hello?
Yes, sir.
You guys attempted the exercises I sent on reduction gearboxes. Oh, so probably some of you haven't touched on them, right? So we are going to look at worm and worm wheels. Right. Once we are done with this section, we will have essentially covered everything under reduction gearboxes. Right. Now, under worm and worm wheels, right? Worm and worm wheels are essentially systems we use to increase a gear system's gear ratio or velocity ratio or its mechanical advantage, right? Now, the way we do that is the worm and worm wheel, right, is a system we use in conjunction with a compound gear train, right? So you would have a compound gear train, right, with however many gears that it has, right? You would have a compound gear train. And then if a need arises for you to increase the gear ratio or velocity ratio or mechanical advantage of that compound gear system, then we make use of worm and worm wheels, right, for exactly that. So to increase the mechanical advantage. So when I say mechanical advantage, gear ratio or velocity ratio, that is essentially one and the same thing, right? So if you're asked to calculate the gear ratio, velocity ratio, or mechanical advantage of a gear system, right, that is essentially one and the same thing, right? So to increase the gear system's gear ratio, right, we make use of a worm and worm wheel system, right? So essentially you will have the compound gear train, right? And then attached to it, you would attach a worm and worm wheel system, right? Now, based on what we've covered so far, right? Based on what we've covered so far, at this point, you understand the relationship, right? If you have two gears in mesh, the relationship between those two gears is one of circumferential velocity, right? The circumferential velocity of gears in mesh is equal, right? So that is to say, the velocity of one gear is equal to the circumferential velocity of the other gear. That's the relationship between the two gears, right? Now, if we look at a worm and worm wheel system, right? This here would be the worm. Meshing with the worm is the worm wheel. So here is the worm wheel, right? Now, if we look at the worm wheel is essentially a gear. But if you look at the worm looks more of a screw than it does a gear, right? So meaning that for the worm wheel, right, we take it as a gear because it is a gear, right? So meaning it will have a rotational frequency n as well as number of teeth, right? But now, if you look at the worm not being a gear, right, uses something else in place of number of teeth, right? Because this being connected to the input shaft, right, or this being connected to the motor, right, is going to have rotational frequency, right? But because it doesn't necessarily have teeth, or because it is not necessarily a gear, right, it doesn't have teeth, right? But we are still able to use something else in place of teeth, right? And that is what we call number of starts, right? So instead of teeth, a worm has number of starts, right? Hence, to get the circumferential velocity for a worm, right, for gears, the circumferential velocity is essentially number of the rotational frequency times number of teeth, right? But seeing that for the worm, we do not necessarily have number of teeth. What we instead have is what we call number of starts. So meaning that the circumferential velocity, right? The circumferential velocity of the worm would be the rotational frequency of the worm times its number of starts, right? So looking at the relationship between the worm and worm wheel, right? Because they are meshing, it means there is a relationship between the two of them, and that relationship is one of circumferential velocity. The circumferential velocity of the worm is equal to the circumferential velocity of the worm wheel. Now, how does that look like mathematically, right? If we say the circumferential velocity of the worm wheel, right, the circumferential velocity of the worm wheel being the rotational frequency of the work of the worm wheel times the number of teeth of the worm wheel is equal to the circumferential velocity of the worm, and the circumferential velocity of the worm is equal to what? Its rotational frequency times the number of starts, right? Now, this is how we look at number of starts, right? If they say a worm has one number of starts, right? So if the number of starts is one, right? If the number of starts of a worm is one, it means that for every one revolution, right? So for every revolution that the worm rotates, right? So if this rotates by one revolution, right, it is only going to engage one tooth on the what? On the worm wheel, right? So the worm having one number of starts means that if we were to rotate the worm by one revolution, right, it's only going to engage one tooth, or the worm wheel is going to rotate by one tooth. So meaning that the if the number of starts of the worm is now two, for instance, right? If the number of starts of a worm is now two, that means that if we were to rotate the worm by one revolution, right, the worm wheel would rotate by two teeth, right? Meaning that if the number of starts is now three, right, this tells us that for every revolution, right, that the worm makes, right, if this rotates by one revolution, if the number of starts is three, it means the worm wheel will rotate by three teeth. Are we clear?
It's a bit
Yes,
confusing,
sir.
sir. Um, um, even if let's say for instance the worm is connected to more than one teeth of the gear.
Yes.
So meaning that the one revolution of the worm just means that one teeth. I mean the gear will to only rotate by one teeth, even though it's connected on all ones are connected on one teeth each. I'm a bit confused there.
So the reason why you're confused is because you are looking at this one, right?
Yes, I'm looking at
If
that one. So
if you
that's
look
the
at
reason.
this
Yes.
one, if you look at this one, they said this is a three-starch worm. Now, if you look at the number of teeth that have been engaged here, right? It's one, two, three, essentially. If you look at this one isn't really engaging that tooth, and this one isn't really engaging that tooth. So essentially, only 3 teeth have been engaged. It's 1,
All right.
2, 3. So meaning if the
Okay.
number of starts was 2, right? Only two essentially teeth on the worm would engage with the what? With the worm wheel. And if it was
With the
1
wormhole.
number of starts, it would only be 1 engaging with the worm wheel.
All right.
I think we are clear now.
No, you're clear, sir. It makes sense.
Yeah. So for this one in particular, because it's 3, the number of starts is 3. That is why you see essentially 1, 2, 3 having been engaged with what? With the worm wheel.
Sorry, sir. If for instance it's not stated that it's a tree start worm, can I then, by looking at the drawing, make an assumption if I see 3, let's say for 3 teeth on the gear I engage with the worm, can I
With the
make that
worm.
assumption that it's a tree start? Yes. Can I make it the assumption to that is a tree start, or it must be stated?
So it must be based on worm and worm wheels, and you haven't been given the number of starts, right? That they want you to calculate the number of starts. If they don't want you to calculate the number of starts, then it means the question is wrong. Such questions exam, right?
All
So you
right.
will never have to assume number of starts.
Okay. Okay. No, it makes sense there.
Yeah. Right. Any more questions? Right. So of starts, right? But the most important thing here is how we use number of starts, right? How we use number of starts is in place of number of teeth, right? So for a worm, because the worm doesn't necessarily have number of teeth, we then use number of starts, right? So for instance, looking at this relationship between the worm wheel and the worm, right? You would then substitute here number of starts being 3, right? In fact, we'll look at this example, right? Now, like I said, a worm and worm wheel is a system that essentially works gear train, right? We are essentially trying to get the compound gear train to increase its mechanical advantage, right? Or its gear ratio or velocity ratio, right? Worm wheel is a worm. Here's a perspective, it seems they are fitted with the same shape. So meaning that whatever.
So you're breaking.
Can you hear me now? Hello.
Yes, we can hear you now.
All right. So, like I was saying, the worm wheel and gear A, right, are fitted with the same shaft. So, meaning that whatever the rotational frequency of this shaft, this worm wheel is going to rotate at that rotational frequency as well as gear A. So, meaning if we were to calculate the rotational frequency of the worm wheel, right, you will inadvertently calculate the rotational frequency of gear A, right? And then gear A, being the first gear in the compound gear train, right? Because essentially how we look at which gears you take as in and which gears you take as out, right, is you first look at where you have the input shaft, right? So the input shaft obviously is fitted onto the what? Onto the worm here, right? So the gear that follows, you are going to take as out. The gear that follows, you take as in. The gear that follows that, you take as out. The gear that follows that, you take as in. And the gear that follows that, you take as out, right? the most important thing here is that your diagram must make sense as far as which gears you take us in and which you take us out, right? Because if this is the input shaft, it means the output shaft is going to be on the last gear, right? So following that analogy, it should work out exactly as how I say, as far as if this is the input shaft, then we know that the output shaft will be fitted onto the last gear in the system. And if that's the case, if you follow that order, right, as to if this is in, right, then the following gear you take is out, follow the gear that follows after that you take is in, the gear that follows that you take is out, and the gear that follows you then take is in, right? If this you had already labeled as out, it should work out, right, following this order that this gear here is what is gear in. Are we clear?
Yes.
Where's everyone else? Hello, people.
Hello, sir.
Yes, sir. We understand.
Right. Right. So meaning that as far as the compound gear train, right, we take this as in, right? So that will be out, this is in, and this will be out, right? And then looking at the entire gear system in its totality, right? Once you establish that that's your input shaft, then you know for a fact that the last gear is the gear that will be fitted with the output shaft. So meaning that for the entire gear system, that's your input shaft, right? And this here is your output shaft, right? So if you're asked to calculate the output shaft of the gear train, right, essentially they'll be asking you to calculate the rotational frequency of gear D, seeing that it's gear D that is fitted with the output shaft. Are we clear?
Yes, sir.
Right.
Yes, sir.
And then if you're asked to calculate the velocity ratio, gear ratio, or mechanical advantage, remember I said that is one and the same thing, right, for gear systems. So if you're asked to calculate the gear ratio, right, between the input and output, again, you look at where is the input shaft fitted. That's your input shaft. It's fitted onto the worm. So essentially, the input rotational frequency would be one of the worm, and the output rotational frequency would be one of gear D. Right? Now let's look at these questions. Right? They said, okay, first let's read the statement. The gear train consisting of a worm and wormwheel is connected to a compound gear train as shown in figure 2.17. Right? You see how they phrased the statement? They said you have a worm and wormwheel that is connected to a what? To a compound gear train. So essentially, you have two systems that are working in conjunction with each other, right? Why? So as to increase the system's what is this, gear ratio or velocity ratio, right? If the three-start worm rotates at 1,200 revs per minute, calculate the following, right? So the worm is a three-start worm, right? And it rotates at 1,200 revs per minute. So essentially, that means the input rotational frequency of this gear system is 1,200, right? Seeing that the input shaft is essentially fitted onto the worm, right? Now they say calculate the speed of the worm wheel in revs per minute, right? Now, as far as the speed of the worm wheel, there's the worm wheel, right? We have the number of teeth of the worm wheel. We are looking for its rotational frequency, right? You look at the gear it is meshing with, right? It is meshing with the worm. Now, what quantities we have for the worm? We have the worm's rotational frequency and we have its number of start. So we can simply just use the relationship between the two, seeing that they are meshing. Right? So we can simply use the relationship between the worm and worm wheel, to calculate what? The rotational frequency of the worm. Right? Okay, let us do this. Let's do this here. All right. Right, number one, calculate the speed of the worm wheel in revs per minute. And as we've established, right, because these two have a relationship between them, seeing that they're meshing, that relationship is one of, what is this, circumferential velocity. The circumferential velocity of the worm wheel, right, the circumferential velocity of the worm wheel, which is NWW, right? So this stands for the rotational frequency of the worm wheel. So WW stands for worm wheel, right? Times the number of teeth of the worm wheel is equal to, so that's the circumferential velocity of the worm wheel is equal to the circumferential velocity of the worm. And the circumferential velocity of the worm is equal to the worm's rotational frequency, right? So the 1W stands for worm, right? Times the worm doesn't have number of teeth, but what it does have is number of starts. So this is number of starts, right? Remember the three steps I taught you in having to calculate, or when looking at two gears in mesh, right? You first establish the relationship between the two gears, and that relationship is always one of circumferential velocity, which we just did, right? Then second, you establish direction of rotation. Now for reduction gearboxes, we don't consider direction, so we can skip that step. And then the third step is to solve for what you're looking for, right? So we've already done the first step. We've established the relationship between the two. Now we are going to solve for what we are looking for. We are looking for the rotational frequency of the what? Of the worm wheel, right? So to get the rotational frequency of the worm wheel, it means we need to divide both sides. We need to divide both sides by the number of teeth of the worm wheel. Right, so obviously that cancels, meaning that the rotational frequency of the worm wheel is equal to this here. Right. Now all we do is substitute. We have the rotational frequency of the worm. It's 1,200. So this is 1,200 times number of starts. They said the number of starts of the worm is 3. This we divide by number of teeth of the worm wheel. The worm wheel has 40 number of teeth, right? So we use here 40, right? Now, I want you guys to punch this in your calculators and tell me what you get there. All right, what is 1,200 times 3 divided by 40?
That's 90.
So this is 90. 90 revs per minute, right? So as far as having to calculate the worm wheel's rotational frequency, this is the simple approach that you take. Are we clear here?
Loud and clear, sir.
Right, this is the approach you take. Right. Now let's look at the second question. Second question is calculate the output speed of the gear train. Right. As we've established, the output shaft is fitted onto the what? Onto the last gear. The last gear is gear D. So if they want you to calculate the output speed of the gear train, it means they want you to calculate the rotational frequency of what? Of gear D. Right. Now, what we've established is that you have the worm and the worm wheel, right? But as far as the compound gear train, right, the compound gear train is from gears A to what? To gear D, right? So you can simply use the relationship between, or the relationship in the compound gear train to calculate what? To calculate the rotational frequency of gear D. right? Now, how are we able to do that? Because the worm wheel and gear A are fitted with the same shaft, right? If you have the rotational frequency of the worm wheel, which we do, you inadvertently have the rotational frequency of gear A, right? Now, in a compound gear train, how do we calculate? What is this? The gear ratio, right? The gear ratio can be expressed in a number of ways, right? Primarily, it is expressed in terms of the rotational frequency, right? Remember that as far as the rotational frequency, the gear ratio is equal to what? The rotational frequency of the input divided by the rotational frequency of the output, right? And then it also can be expressed in terms of number of teeth, right? Now, for a compound gear train, right, how we express the gear ratio in terms of number of teeth, right, is by looking at the product of essentially T out divided by the product of the number of teeth of gears we consider as in, right? That is where having to label your gears accordingly as far as which gear you take as in and which you take as out comes or is convenient, right? Now, taking that into consideration, right, we are looking for the rotational frequency of the output. The output we've identified, right? The output shaft will be fitted onto gear D. So gear D is essentially our output, and then our input for the compound gear train is gear A. So essentially here, you can express this as NA, which is the input, divided by ND, which is the output, is equal to product of T out. Then you look at which gears you've considered as being out here. Gear B and gear D are both out. So essentially the product of that will be TB times TD. So this will be TB times TD divided by the product of T in. So you look at which gears have we considered as being in, right? Gear A is in and gear C is in. So meaning the product of that will be TA times TC. So here you will have TA times TC, right? Now, based on what we have here, right, we are able to get the rotational frequency of A, right? Remember that gear A and the worm wheel are fitted with the same shaft, and we've just calculated the rotational frequency of the worm wheel, right? So essentially, we have this. This is what we're looking for, and we have all the number of teeth, right? If you look at our diagram, they've given us all the number of teeth, right? We have the number of teeth of A is 21, for B is 48, for C is 14, for D is 28, right? So now it's a matter of manipulating this such that we make ND the subject of the formula. So making ND the subject, right? ND divided by essentially NA is equal to TA times TC divided by TB times TD, right? All I did here was switch the numerator and denominator, right? And then making ND the subject of the formula, it means we have to multiply by NA both sides. So when doing that, we then get ND as being equal to TA times TC times NA divided by TB times TD, right? Now all we do is substitute. So in substituting, we now look at the number of teeth of A. Number of teeth of A is 21 and the number of teeth of C is 14, right? So essentially this is 21 times, so this is 14 times NA. NA is fitted with the same shaft with the worm wheel. The worm wheel, when we calculated its rotational frequency, we got 90. So this is 90 divided by TB times TD. We now look at the number of teeth of B and D. It's 48 times 28. So this is 48 times 28, right? Now, when you punch this in your calculators, what are we getting? What do we get? Hello?
I'm getting 19.688.
So 19,688 revs per minute, right? Which makes a lot of sense. If you look at, so the reason why I say it makes a lot of sense is because this is a reduction gear. What is this? This is a reduction gearbox, right? Now remember with reduction gearboxes, right? Um, it is called a reduction gearbox because of its purpose, essentially, right? The purpose of a reduction gearbox is to reduce the rotational frequency of the gears, right, from the input to the what, to the output shaft, right? Now, as you reduce as the system of gears reduces the rotational frequency of the gears, right, it inadvertently increases the output torque, right? So essentially, the purpose of a reduction gearbox is to increase the the torque, right, such that the system of gears is able to output the most torque from the system, right? So to output the most torque in the system, right, the trade-off is that the rotational frequency of the gears from the input to the output shaft, right, has to reduce, right? So it makes sense in that sense. Why? Because if you look at the input shaft is rotating at 1,200 revs per minute. So the drop from 1,200 to 19,688 revs per minute is a significant one, right? Hence, even if at this point you think of how this affects the gear ratio or velocity ratio or mechanical advantage, right? It seems we are going to get a very ridiculous amount of gear ratio or mechanical advantage, right? Which is essentially why we use worm and worm wheels, right? To get a ridiculous amount of mechanical advantage, right? So that's how you do number 2. When you look at number 3, they want us to calculate the gear ratio between the inputs and outputs, right? Now, when they want you to calculate the gear ratio of the inputs and outputs, right? The input here is this one, the one fitted to the worm, and the output shaft, as we established, is fitted onto gear D, right? Now, to calculate the gear ratio, this is number 3, right? So this one, they could have asked you to calculate the gear ratio or velocity ratio or mechanical advantage, right? Either way, you will take the very same approach we're about to take, right? So they said gear ratio, so we use gear ratio. Gear ratio primarily is expressed in terms of rotational frequency, right? We've identified that the input shaft is fitted onto the worm. So essentially, this being N in, this will be N worm divided by N out. And we've already established that the output shaft is fitted onto gear D. So this would be ND. And this is what would give you the gear ratio, velocity ratio, mechanical advantage, right? The rotational frequency of the worm is 1,200. All of this divided by the rotational frequency of D, which we calculated and got 19,688. Right. Now see what you get. All right. So what are we getting?
Sixty comma nine five two, sir.
So 60,9. So I'm getting 951.
Yes, it's 951.
Right. So this is going to be is 1. Right. So remember your gear ratio. Right. You must make sure that you have the is 2. Right. So for this case, it's going to be is 1. Right. As you can see, The gear ratio is 60,951, right, which is not normal for a gear ratio, but very normal for a gear system that has used a worm and worm wheel, right? So this here is the reason why we use a worm and worm wheel, to increase the gear system's mechanical advantage, velocity ratio, gear ratio. Are we clear here?
Yes, sir. Be clear.
Right. So as far as worm and worm wheels, this is the approach we take for these kind of problems. Right. Are there any questions before we move on? I will be sending this in the group. Any questions?
All good, my side.
It seems someone has a question. Does someone have a question there? Oh, they were saying no, sir. Okay. Okay, then.
Sir, I've also got one, sir.
Okay.
Sir, what was that of the wormwheel? That was yes, there's the question. The three star. Yes, sir. Is that the number of teeth that it's engaging, or what is it that engages with the output, the wormwheel?
So a 3-star is essentially, it is essentially the number of teeth on the worm that engages with the what? With the worm wheel.
Okay, I understand, yes, sir.
Yeah, so if it's 2, it means only 2 engage with the worm wheel. If it's 1, it means only 1 engage with the worm wheel.
Yes, sir.
Yeah. So meaning that if this rotates by 1 revolution, right, you have a 3-start worm, right? So if this rotates by 1 revolution, right, it is only going to move by 3 teeth on the what? On the worm wheel. So for each revolution, right, the worm only rotates by 3 number of teeth.
Okay, yes, I understand, yes, sir.
Yeah. Any more questions?
Just one question, sir. I tend to be confused when it comes to notation. Like you'll find the rotation of the worm wheel, you denote it as NWW. Then the rotation of the worm, I don't know whether it's a worm or
Yeah, it's a worm.
NW. So it's worm. So it's a bit confusing for me there.
In the
to
test,
get used to
Alex,
it.
So we only used this notation because they didn't necessarily name the worm wheel, right? If you look at the other gears, this is A, that's B, that's C, that's D, right? They didn't notate this one, right? So that is why I used this, right? But probably in the test or exam, you are going to get this will be named as some letter, right? Just like the other gears, and that is what you would use. Like for instance, if they said this is gear E, right? So this would be instead NE as opposed to using NWW.
Noted, sir. No, I was a bit worried because I know notations can confuse sometimes.
Yeah, it's only this one that is always named as a worm, right? So for this one, you can simply just use NW for worm.
All right. Thank you, sir. Thank you for clarity.
Yeah. Any more questions? Right. So make sure you understand worm and worm wheels before Friday. If you catch my drift here.
We'll try, sir.
All right. Right. Now let us look at one more problem on epicyclic gears. Epicyclic gears is this problem I wanted us to do. Let me see. All right. Epicyclic gears.
Oh, sir.
Yes.
I have a problem here with my phone and my. The screen is just dark. Is there any another way that I can watch this video?
I'll be uploading the video on my channel, so you can catch it there.
Okay. Thank you.
All right. Sorry, man. Okay, let us do unable. Huh? What happened? Oh. All right, let us look at this particular problem. All right. Let us look at this particular problem. Right. Now, I don't know if you guys remember, but in the session we had when we looked at epicyclic gears, right? I said you get epicyclic gear systems that have external gears, right? That are not necessarily part of the epicyclic gear system, but we make use of them because a particular system requires that you have the input shaft fitted onto an external gear, right? For whatever reason, right? That reason could be you want to have some form of rotational frequency on the either the planetary gear or sun gear, or you want the arm to move at a certain rotational frequency or certain direction, right? Now, this here is one of those cases where you have, now, if you look at from this gear, the analysis, right? So this here is essentially a typical epicyclic gear system, right? A typical epicyclic gear system is one that has an analysis, the arm, planetary gear, as well as the sun gear, right? So this here is the analysis, right? Meshing with the analysis, you have so meshing with the analysis using the internal teeth, right? You have the planetary gear, right? They've labeled it as gear P, and then meshing with planetary gear is the sun gear S, right? So essentially, we're looking at a typical planetary gear system, right? With an external gear. Why do we have an external gear? Because for this particular system, right, for this particular case, right, they needed to fit the input shaft onto an external gear, right? Maybe that was to frequency as well as direction of the analysis, whatever the case, right? For this particular case, they needed to fit an input shaft onto an external gear, right? So this external gear, right, isn't necessarily part of the what of the epicyclic gear system. So in turbulating your information, you wouldn't turbulate this external gear, right? Just like the case we looked at based on bevel gears. Remember, under bevel gears, you get two types of gear systems. You have a an epicyclic gear train made of bevel gears, and then you have a humpage epicyclic gear system, right? For a for an epicyclic gear train made of bevel gears, remember there is a gear that we treat as an external gear, right? That is the one that is fitted with the input shaft, right? Whereas with the humpage epicyclic gear system, right, N and all gears we take as being part of the epicyclic gear system. Hence, we turbulate all the gears, right? So essentially, this you would treat the same way you would treat an epicyclic gear system made of bevel gears, right? The relation between the two is that you have an external gear, and that external gear is used to fit what? To fit the input shaft, right? So Knowing that for epicyclic gear systems, you have to tabulate your information, right? You know by now, first and second condition are fixed. So meaning that the first and second condition do not change, right? They are not necessarily dependent on what is being asked or what is being given, right? To get the first and second condition, you just need the number of teeth, right? And then you just follow the 3 steps, right, in completing the first condition, right? And then in completing the third condition, remember that you need 3 things. You need what you are looking for and 2 other assumptions, right? Now, the external gear, right, we use to get one of the 2 assumptions you need to complete the third condition, right? Now, for instance, here, if you look at the external gear, right, it has been labeled as gear B, right? You would use the relationship between this external gear B and what? And the annulus, right? If you look at the annulus has teeth ground onto it on the inside true circumference as well as the outside true circumference, right? So essentially, the external gear is meshing with the annulus, right? Using the annulus's essentially gear E or external gear teeth, which is the 90 teeth, right? So you would use this relationship between the 2 meshing gears, right, to calculate what? To calculate the rotational frequency of the annulus. And that rotational frequency of the annulus, you would then use as one of your assumptions in your third condition, right? Now, for instance, here, if you look, they said calculate the speed of the annulus, right? Number 2, the speed and direction. So number 2, you can do on your own. Number 2 is where you have to tabulate information and establish the third condition, right? The most important thing here that I want to show you is number 1, right? Calculate the speed of the annulus, right? Calculating the speed of the annulus, right? That is the rotational frequency. So we have to look at which gears the annulus has a relationship with that we can use to calculate the speed of the annulus, right? And that relationship will always be with the external gear teeth. External gear, right? If you look at the external gear, it's fitted with the input shaft. The input shaft is rotating at 250 reps per minute, right? So because it's positive, we are going to take it as clockwise. So we have a relationship between gear B and the annulus, essentially gear E, right? So to differentiate between the internal and external teeth, right, they have named the internal as gear A and the external as gear E, right? But both are on the what? Are on the annulus, right? So having to calculate the annulus, we establish the relationship between the gear it is meshing with gear B, right? So the relationship between gear B and the annulus is what? Is that the rotational frequency of the annulus, right? Seeing that gear B is meshing with the annulus using the external teeth. The external teeth here have been labeled as E. So this will be E times the number of teeth of E is equal to, it is meshing with the external gear B. So NB times TB, right? That is the relationship between the 2 gears, right? Remember, 3 steps. First step is you establish the relationship between the 2 gears, which we have. So next thing is you establish direction of rotation, right? Now we've already established that the input shaft is rotating at this, right? So seeing that it is positive, it means it's going clockwise, right? Now the 2 gears are meshing with the outside true circumference, and gears that mesh with the outside true circumference, right, go in different directions. So if this one is going clockwise, it means the annulus is going anti-clockwise, right? So it means NB remains positive because it's going clockwise, and then NE we write as negative, seeing that we've established that it will be going anti-clockwise, right? That's step number 2. Step number 3, you solve for what you're looking for. We are looking for NE, meaning that to make NE the subject, we have to divide both sides by negative TE, right? And then obviously that cancels. Therefore, meaning NE is equal to NBTB divided by negative TE. Right? Now all you do is substitute. NB is 250 revs per minute, so that's 250 times TB, the number of teeth of gear B, external gear B is 26, so that's 26 divided by negative number of teeth of E, that is 90, so that's 90. And what do you get here?
72,222.
All right, so remember the sign, people. So it's actually negative 72,222, right? And then you would rewrite this as 72,2 recurring revs per minute anti-clockwise. Very important to indicate the direction, right, for epicyclic gears, right? So you do not leave your answers as just negative or positive, right? If your answer is negative, right, you then rewrite it and then you indicate the direction. Are we clear?
Loud and clear, sir.
Right. So for this particular case, once you've established the rotational frequency of the annulus, right? So for number 2, in completing the third condition, right, this is going to be one of your assumptions, right? If you look at the statements, they said in the planetary gear system shown in figure 1.21, the external gear B driven by the input shaft rotates is 250 revs per minute. It meshes with the 90 external gear teeth on the annulus E. The annulus A has 64 teeth, has 64 internal gear teeth. The sun gear S has 36 teeth and is fixed to the casing, right? So that is one of the assumptions you are going to use in your third condition, right? It meshes with the planet's gear P with 14 teeth. The lever arm is connected to the planetary gear and rotates the output shaft, right? So remember, they said for number 2, calculate the speed and direction of the output shaft, right? The speed and direction of the output shaft, right? The output shaft, they said the lever arm connected to the planetary gear and rotates the output. So essentially, if they want you to calculate the output shaft, they essentially want you to calculate the rotational frequency and the direction there of the lever arm, right? So out of the 3 things that you need to complete the third condition, you have what you're looking for. We are looking for NL, right? So here you're looking for NL, right? So you have what you're looking for. Now you need 2 other assumptions, one of which is going to be this one here, that's NE, right? The annulus, right? So the annulus, remember at this point you would have used NA. So essentially it's NA, that is, what is this? What is this? 72,222 revs per minute. And then the third one is this one here. They said the sun gear has 36 teeth and is fixed, right? So essentially NS would be equal to 0, and that would complete your third condition, right? So the point here is that this year, once you've calculated this using the external gear, this you can use as an assumption, right, as one of your assumptions in completing the third condition. Are we clear here?
Loud and clear, sir.
Right. So I just wanted to highlight that part. Right. Are there any questions?
On my side, all good, sir.
What about others? All right. I'll take silence.
I think with more practice as from today till to the test. I think we'll raise some questions. We'll touch on the side.
All right.
Don't mind.
No, that's fine.
Thank you, sir.
I'm totally fine with questions. I like questions, in fact. It shows people are actually doing the work. All right, people.
Thank you.
Make sure what we cover today you go over as well, right? And then, of course, those that haven't watched the video on belt drives, make sure you watch that video, right? On the test, you can expect belt drives. Conveyor belts will be in the second assessment, right? So because of time, I would say don't waste time looking at conveyor belts, right? We will look at that again, right, before your second assessment. Are we clear?
Yes.
Yes.
All right. All the best to you guys. All right. Good luck for Friday.
Sorry,
So,
sir.
quick question.
Yes. Lady first.
You can go first.
Okay. Can you please make sure when you write on Friday that we have the formula sheet? Because yesterday we didn't have a formula sheet. The lecturer forgot to attach it.
Yeah, you will never have those kind of problems with Mr. Mteto.
Okay.
Okay, so I just wanted to find out. There's some theory in this text. We see it's quite a bit of theory. Will we have to know theory work as well?
In the exam, yes.
Okay, and for the 4th week test,
Nah.
is it just the calculations? Or okay.
Yeah, it's
Thanks,
calculations. There's something I don't remember. So there's one thing, but I don't necessarily regard it as a theory. You know, questions like, for instance, if I ask you to name the 4 main parts of a typical epicyclic gear system, would you regard that as theory?
Not really.
Exactly. So I just don't remember if I have that kind of question, right? But if there is any kind of theory, it will be such questions. So no, there's no theory in the test.
Okay, thanks, sir.
Sure.
The question.
Yes.
Sorry, you gave us an example. You gave us a handout, example 2.4 with the reverted gearbox. I understand first gear and second gear. Just tell me the power flow for third gear. Thank you.
Was it?
It's called, yeah, it's example 2.4, and it's a 3-speed reverted gearbox.
Right. So
and you gave us the memo for the first gear. I understand the second gear. I just want to know the power flow for the third gear. Is the third gear only E and F? Thank you.
So with with gearboxes, right? If you have a 3-speed gearbox, right? Essentially how a gearbox works is that in the last gear, right? So if you're looking at a 3-speed gearbox, the last gear is what is the third gear. In third gear, the input shaft and output shaft, right? They mesh. So at that point, the gear ratio is 1:1. That is why I didn't touch anything based on on third gear, because the gear ratio is 1:1, essentially. That is why we are more interested in the gears that mesh in first gear as well as second gear, because in third gear, we know that the input and output shaft essentially mesh. And when they do mesh, the gear ratio is 1:1.
Thanks, sir. Thank you.
Sharp. Any more questions? So that is to say, if you're looking at a 4-speed gearbox, right? You would have a gear ratio for first gear, second gear, and third gear. And then in fourth gear, that is where the input and output shaft mesh together, making the gear ratio 1:1, right? Are we clear?
Thank you, sir. Thanks.
Sure. Any more questions? Okay. Let us call it tonight, guys. Well, I'm calling it tonight.
Sorry, sir.
Yes.
I was looking for this question now that I've got, sir. It's in the summative assessment for module 2. This is also a 3-speed gearbox, but in the question, I'm trying to do question 4.2. They give me the module and they say the module is more than 6, but less than 10.
Right.
That is on page.
So for those kind of questions, just get the average. So if it's more than 6, more than 10, add the 2, divide it by 2.
They say more than 6, less than 10, sir. So what will that be? 8?
You can use 8, you can use 7. They said, what did I say?
They say if the module for gear wheel C and D is more than 6 but less than 10.
Right. So at that point, you can use 7, 8, or 9. All of those are more than 6.
Okay, so
It's
okay.
it's actually a ridiculous question. I doubt you would ever be asked such a question in the definitely not in the test. It's a ridiculous question because if you ask such a question, then you would even have to account for someone who uses 6.5 because that's still more than 6, less than 10. So it's a ridiculous question.
Okay, sir.
Yeah, I wouldn't worry about the question if I was you.
Okay, thank you, sir.
All right. Any more questions? Right, beautiful. Right, so make sure you do that example, that exercise on worm and Wormwheels in that in the documents I sent you for the tutorials and reduction gearboxes. Right, and then of course you can discuss amongst each other to see if the approach is the right one. Right? Good luck with your tests.
Thank you. Bye.
Thank you, sir.
All right, cheers.
Bye-bye.